Dror Baron is an associate professor in the Department of Electrical and Computer Engineering at North Carolina State University. His research lies at the intersection of fast algorithms, signal processing, and information theory. Dror, thank you so much for taking the time today.
Joe, thanks for inviting me.
So, to start, can you tell the audience a little bit about your research related to quantum computing?
Sure. I was working on what we call classical problems. Classical meaning pre-quantum for many years, and as you said, statistical signal processing, information theory, topics along those lines. Some people in 2025 would say that it's correlated to AI, but I actually don't view myself as working on that. And in 2021, after wanting some change of scenery, I shifted to quantum topics and I started studying about quantum computing and quantum information. And one of the things that I've seen over the last 4 years, and I've also been working on, I appreciate that there are many things that I worked on in my classical past that are actually very, very useful in the quantum space. And that is that explains some of the contributions that I've made over these years, really based on uh, things that I knew very well that the the quantum people it would have been quite a challenge for them to learn the material, and for me, I already know the material.
So, can you talk a little bit about those classical foundations and what you drew from that body of knowledge and applied to quantum?
Yeah, certainly. One of them is so information theory deals with fundamental performance limits of communication systems. Let's kind of try to unpack the words. By fundamental performance limits, it's like what's the best possible that can be done? What cannot be done? Ideally, we want to have a clear understanding of this is the limit of what can be done based on the laws of nature, the probabilistic properties of a communication system, et cetera. So best trying to understand the best possible. And then another aspect here is that because these are performance limits, best possible, it might not be computationally feasible. So traditionally, information theory researchers, many of them still do, they ignore the computational aspects. So they're saying, from the point of view of the information that we're given, what's the best information processing quality that can be attained? And just to give a quick example, uh, here's my phone, and the phone communicates in a very complex electromagnetic space. But suppose that we would model this mathematically in a much simpler electromagnetic type of environment. So information theory researchers would study what's the best possible rate of information at a certain transmit power that we can communicate efficiently over over an electromagnetic channel that's characterized, as I said before, by under whatever model that they would be assuming. That's one part of the unpacking. The other part of the unpacking, I said communication system. So communication system is, well, could be a phone, but it can also be storage. So if maybe not in 2025, but if we had this conversation in 2005, we would probably be storing data on DVDs or CDs or something like that. And there has been a lot of information theory work on uh, performance limits of storage. And you can imagine that when you begin by looking at the fundamental performance limits, a few steps down the road, you also do start thinking about what's maybe not the best that we can do. What's the best that we can do in practice with reasonable computational constraints? So again, I'll use the word classically. Classically, information theory people ignored the computation. They assumed that computation was for free. What's the best that we can do? But then when it goes from just a bit from a purely theoretical investigation to just a bit toward the practical side of the spectrum, people do start asking these questions of what can be done computationally in practice given current constraints. So I guess
So
that was a pretty long answer, but I hope I gave you insight.
yeah, so I'm curious, what is quantum enabling us to do now related to both the communication and storage and anything else?
Oh, that's a great question. There is an area called quantum information theory that asks similar questions. And um, earlier I mentioned the word channel, electromagnetic channel. So you have a phone and it transmits an electromagnetic waveform, and that waveform gets distorted by the environment and corrupted by noise and interference from other phones and other transmitting devices, etc. Similarly, in the storage space, maybe you'll have a CD or DVD, or nowadays it might be people might be analyzing um, semiconductor storage device, whatever it is, and they're modeling a channel. A channel is basically the process where you have an input, it's corrupted or distorted, interfered with, then you have an output and you're trying to recover the input from the output. In the quantum world, the channels are quantum in nature. So we need to be aware of the basics of quantum mechanics. Now, quantum mechanics, on the one hand, um, it is counterintuitive, like a lot of ideas such as superposition and entanglement that people hear about. They're very counterintuitive. They're different from our day-to-day experience. When I started learning about this stuff in 2021, I to be honest, I was astonished by some of the things that I learned. It was I I heard of something of some effect, and I in my mind I tried to make a mental picture and I tried to understand it. And then a week later, I learned that no, that understanding is wrong.
Hmm.
And I ended up going along the lines of a well-known quantum physicist, David Merman, that he said he had the famous quote, "Shut up and calculate."
Hmm.
And what he meant was that instead of trying to have an intuition about the quantum mechanics, which is maybe not hopeless, but very difficult, better to just sit down, calculate, go through the math steps. And I do quote that I do quote him in my quantum course. So basically, to answer your question, quantum information theory takes these uh, the quantum mechanics. You model a channel, the corrupting mechanism, and now you're asking, what's the best that I can do with a quantum corrupting mechanism?
So can you talk about that a little bit more in terms of application of like how does that impact people in their everyday lives, or how could it in new technology and in the way we communicate and the way we share information? Is this something that is already being implemented in our daily lives and the technology that we
A
use?
lot, a lot of the quantum things are in contrast to, I know that you discuss AI with a lot of your interviewees. And in contrast to AI, which is all around us in applications, and it's perhaps not very mature, but somewhat mature, quantum is uh, at an earlier stage. They're beginnings of applications in very narrow segments of the economy, but early innings. And I'll describe what could be a future application. You'll have a quantum computer. You told me earlier that you're in the Washington, D.C. area, and I'm 300 miles to your south in Raleigh, North Carolina. And suppose that you have a quantum computer and I have a quantum computer, and we want to exchange information. So, quantum information theory would tell us that there will be some quantum network, probably swapping photons or something like that between these cities, probably on an optical link. This is not my area, so I'm kind of improvising, but it would tell us what's the most efficient way of swapping information between our quantum computers. And because again, this is based on the rules of quantum mechanics, we could entangle some particles that I have on my quantum computer and some particles on your quantum computer. And just to explain intuitively, I said earlier, shut up and calculate, but let's try to be intuitive. Entanglement is a fancy way of saying that if anything happens to my particle, it'll have an impact on your particle instantaneously. And instantaneously meaning truly instantaneously. So one interpretation of that when people were learning these things in the early part of the 20th century, people were very bothered by, can this break the speed of light? So that's not the right interpretation. An interpretation that I heard later that, to me at least, is more intuitive, is that we're not communicating, we're not, the state of matter between our particles in Washington and Raleigh is not being transported. What's actually happening is that information is being coordinated. Information changed in my quantum computer, and it immediately is coordinated your quantum computer because these particles are entangled. So they coordinate themselves. Their quantum states are changing together.
Hmm.
And as I said earlier, for most of us, certainly for me, it is very counterintuitive to think about something that is hundreds of miles apart and will instantaneously change. But there have been a number of experiments. I believe in 2023, Aspect, a French physicist, got the Nobel Prize in Physics. So these things have now been confirmed experimentally again and again and again and again. And it sounds, to me at least, super, super weird. But that is because we are humans who are operating on a macro scale, and these things are operating on a tiny, tiny scale. So it's just, we don't see this on a day-to-day level. We don't see this, and that's why it's hard for us to understand it.
Yeah. Well, I also wanted to ask you a little bit more about some of your research related to quantum error mitigation. Can you describe for the audience what is quantum error mitigation?
Yeah. So the way how I think it's possible to understand it is that you're going to have a quantum computer. Okay, what's a quantum computer? You have a bunch of these particles, and you might be zapping lasers at them, or you might have electromagnetic fields, uh, whatever it is, in order to manipulate the states of these particles. And because there is entanglement and interference, and it's very a very fragile environment, a lot of the quantum computers, we need to operate them at very low temperatures. And by very low temperatures, I don't mean 0 Fahrenheit or minus 100 Fahrenheit. I mean like millikelvin. So Kelvin, in that scale, 0 degrees is the absolute minimum. And we're talking about a few thousandths of a degree above the absolute minimum. So it's super cold. And to do that, they have multiple layers of refrigeration. Okay, so now you have a quantum machine, like a chip, basically similar to a computer chip, just operating on quantum effects in the middle of the fridge, and you give it commands. You meaning you're outside, you're sitting on your laptop, and through a web interface, you're controlling the quantum chip, and it's doing stuff, and then you're reading things back and you're processing it. But again, it's noisy. And in 2025, in the classical world, we use transistors to manipulate bits meaning zeros and ones. In the classical world, from what I've heard, the transistors, their error rate is something like 10 to the power of minus 27. And I calculated that 10 to the minus 27 means that my laptop, that I'm tapping on it now, it has tens of billions of transistors, and they're order of a billion operations per second. Most of the transistors are not going to operate like every clock. Every clock, like the fraction of transistors that will switch states is very, very low. But I calculated the 10 to the minus 27 means that until my laptop is basically old and about to die, there will not be a single error. Zero. Perfect. And in contrast, the quantum devices, the best manufacturer that I'm aware of, they achieve something like 10 to the minus 5. And a lot of the other manufacturers, the 10 to the minus 5 is on simpler quantum operations. On the more complicated quantum operations, 10 to the minus 2 is more typical. So 10 to the minus 2 meaning 1%. There are a lot of errors. So now imagine at a high level, I have my chip, I'm running quantum operations on it. I ran several hundred of them or several thousand. It's quite likely that a few errors happened. And we in the classical world, we can only observe the quantum phenomena by measuring at the end. And when you measure, a simple way to think about that is that at the output, we get bits, ones and zeros. So the quantum world operates in qubits, which are superpositions of zeros and ones. But at the end, we can only observe 0 and 1. That's imprecise, but it's an okay way how to think about it. Okay, so imagine that I have 100 zeros and ones at the end. So I have like a string of 100 binary digits. However, because of all the noise, the string will very often be wrong. So quantum error mitigation deals with the problem of what do I do when the string is wrong? Now, what people have been doing over the last several years, they run the quantum machine many times. And they run it many times, and hopefully some of the time they'll get the best answer. And by running it many times, they'll get enough information to be able to know what to do. And that has some pros and cons. So we had my first quantum paper in beginning of 2024. We analyzed a quantum algorithm that has only one correct output, and one correct output meaning if we ignore noise. And there are quantum algorithms that have a single correct output. Most of the quantum algorithms have many possible correct outputs. So it's not like in the classical world where there's one correct output. The quantum, because of all the quantum effects, interesting things can happen. Okay, but suppose you have one correct output. But because of noise, you're seldom going to measure that. So imagine that you have 100 of these bits, and imagine that 5% of them are going to be flipped when you measure. And the 5% number that I just said, it's actually, that's sort of what we're seeing on some quantum computers. So I'm not totally making up the numbers. But then if on average we're flipping 5%, that means that on average 5 of the bits are going to be flipped. Now sometimes I'll get lucky and 0 will be flipped and I get that one correct output perfectly. Other times 8 or 9 will be flipped, but on average 5 will be flipped. Now getting to observe the 100 perfectly, if the average is 5, it'll happen something like 0.5% of the time. Details are not important. So if I run my algorithm 1,000 times, I'm probably gonna be measuring that truth a few times, and everything else that's measured will only appear once. So now I know, okay, I have this one output, 100 bits. I generated 100 bits 1,000 times. One of these 100-bit strings appears 4 or 5 times. All the others appear a single time. Okay, that one that appeared 4 or 5 times is very likely the correct one. So that at that level, for that example, taking the one that appeared the most times makes sense. However, if you go from 100 bits to 1,000, and on average 50 will be flipped, you're never going to be measuring that perfect thing. So that's one complication in error mitigation. Another complication, error mitigation, I said, for quantum algorithms that have a single output. As I said, sometimes that's correct. Most quantum algorithms have numerous possible outputs. So our next step, which we published, we put 2 papers online earlier this year, was multiple quantum outputs. So you can already see that when you move from this really, I'll call it, okay, calling it easy may not be. I mean, the quantum world is complicated. When relatively easy, when you move from this relatively easy problem of I have a single correct output, 100 bits, and if I measure it 1,000 times and 5% of the bits will be flipped, okay, that's reasonable. Moving to I now have 10 possible outputs or 1,000 possible outputs, or every single string of length 100, all these bit strings could be measured, but some of them have higher probability than others. Or to be fair, a small number of them have a higher probability, and the overwhelming majority of these bit strings are, practically speaking, you're never going to see them. So when you move to more complicated quantum algorithms that have that type of characteristic, and you have measurement noise, and in the measurement noise there might be, because of the nature of the quantum mechanics, maybe an error on the 17th bit is correlated to an error on the 18th bit. So when you go from these very simple quantum algorithms and very simple models for how the output is corrupted to more complicated corruption mechanisms and more complicated quantum algorithms, things get complicated very quickly.
Yeah.
Let me just mention one thing. The reason why this is useful, you were asking about, people sitting at home and watching this video and how not in 2025. Well, people are actually running these algorithms in 2025, but think about 2035. The reason why this could be useful to people is that at this time, every time that we run a quantum algorithm, it's called a shot, a sample or a shot. And if you go to Amazon bracket, you'll see that Amazon is selling runtime under the AWS ecosystem, just like they're selling runtime of regular classical computers. They're selling runtime of various quantum computers, quantum companies, and it's on the order of 1 cent per shot. Some of them are a bit more, some of them a bit less, but call it a cent per shot. And in the example that I had earlier, 1,000 shots, 1,000 cents, $10. I hope that for most of your viewers, if you have some important problem that you want to run a quantum algorithm, $10 is okay. But what if I need 1 million? That's $10,000. Joe, I don't know about you. I don't want to spend $10,000 on one computation.
Right. Yeah.
And that's probably true for the large majority of our viewers.
Yeah. So is that cost easily controlled, or is that something that we can plan in the long term for a reasonable cost for these computations to be able to happen, or how do you think about that?
Again, a great question. I'm sure that as we move forward in the conversation, we'll talk increasingly about the future of quantum computing. And the trend is that as the number of qubits, the number of particles is increasing, we use schemes called quantum error correction to basically reduce the rate of errors, the number of errors. And in the classical world, we practically speaking, we need to use error correction just a bit in storage. If I want to store my, let's say, earlier we were chatting and I told you that I have a parrot and we take her videos sometime. And if I want to store her videos, which is many, many megabytes of data, and I want to store it for years, then there's a bit of error correction that the operating system is using in order to minimize the possibility that that data will be corrupted. And if, again, my phone, I'm moving information over this very complicated electromagnetic channel, we use error correction. But on the actual calculations, our transistors are so good that I'm sure that for some of the space systems with chips that they send into space, I'm sure that they use some error correction. But on our regular phones and on our regular laptops and desktops, no, no error correction for the computation, or maybe minimal in special applications. In the quantum world, on the other hand, because the devices, as I said earlier, have 1% error rates, in the bad case, in the best case, 10 to the minus 5 now. We, I don't want to say that we very much want to use error correction if we want to work on large problems where we make millions of calculations, millions of quantum calculations. So the trend is, as we have more qubits, we can apply error correction, which requires overhead in terms of the number of qubits. Simple way of thinking about it is I'll have one qubit, but I'll have 5 copies of it, and I'll take a vote of the majority. That's a naive way of thinking about it, but it's one of the simplest quantum error correction approaches. And the more complicated ones are, well, more complicated, of course, but similar to the idea of 5 to 1, you need more physical qubits. And as we have more physical qubits on our devices, that's been the trend. We can use more powerful forms of quantum error correction. And that is widely believed to be the trend over the next decade or two, that there will be devices with more qubits, and then there will be better error correction. But error mitigation addresses primarily the case where we're either not using error correction or very mild error correction. And the devices are still very noisy. So what do? You don't want to pay $10,000 for running that computation a million times. You want to pay $100 by running it 10,000 times. So quantum error mitigation is believed to be able to give you that factor of 10 or 100.
So you mentioned a couple times the noise. I also wanted to ask you about another facet of your research. What is noise-aware unsupervised learning?
That appears in the title of one of the recent papers that we had earlier this year. I think I said that we had 2 recent papers that we went from modeling a quantum algorithm with a single correct output to a quantum algorithm with multiple correct outputs. And as I said earlier, there are more of these algorithms than the ones that have a single correct output, but there are even more that basically anything could be output, but just a few of them dominate the probability. But we're moving from the simplest case to more complicated cases. And the paper that you just mentioned, a few words from its title, the unsupervised part, that's a term in machine learning. And it means that I have data, and supervised learning means that somebody is telling me what my data means. Somebody's interpreting the data. So for example, Google might have data about how a person is browsing and possibly clicking on ads, what the ad is, what their browsing history is, et cetera, et cetera. But what interests them presumably is whether they clicked or not. And if they clicked, how many dollars of revenue came out of that click. So they have, in addition to all the predictive information, they also have the outcome. And that is supervised learning, where you have in the data the outcome. So it's kind of supervised by, the result. And you're trying to learn the function that predicts whether you'll click or not, but in the training data, whether they clicked or not. Unsupervised learning is where you don't have the result. All you have is data, and you're trying to understand the structure of the data. So what we did in this paper, we performed quantum error mitigation where we have data. The data were these, again, 100 bits, ones and zeros, and I'm collecting perhaps 10,000 versions of them. So now I have 1,000,000 bits. I have 100 bits 10,000 times. It's not the same 100 because it's noise. It's also not the same 100 because I have multiple possible outputs to my quantum algorithm. And the unsupervised part means that I'm now looking for clusters in my data. Clusters meaning I'm looking for vectors of 100 bits that are close to one another. And if I have 5 possible correct quantum truths, then probably around those 5 actual truths, I'm going to have 5 clusters. And then within each cluster, the paper that I mentioned from 2024, it gives it gives some theoretical reasons to take the cluster and then look at the 100 bits, bit number 1, bit number 2, up to bit number 100. And suppose that in that cluster I have 1,000 strings. So in bit number 13, I have 1,000 bits. And in bit number 80, I have 1,000 bits. Each of them I have 1,000. And I'm now going to take the majority. For bit number 13, suppose that 600 were 0 and 400 were 1, I'm going to vote 0. And for bit number 80, suppose that 300 zeros and 700 ones, I'm going to vote 1. So this majority vote, bit by bit, turns out to have some theoretical optimality properties in the simple case of a single correct output. So we use that on the more complicated case. So first we're performing clustering, and that's the unsupervised word. And after we perform clustering, we take a majority vote. And again, it's theoretically motivated, and it works pretty well on real data.
Yeah. Well, so is machine learning and I guess artificial are these technologies being integrated with quantum computing, or how is this you mentioned machine learning, is that becoming more and more just a part of uh everything that's happening, or how do you think about that?
I guess the answer is yes, yes, yes. And as you know, in 2025, people are trying to use machine learning in many, many areas. And in my mind, one interesting way how machine learning is being applied is that, and this is called quantum machine learning or variational quantum algorithms. So you have a quantum circuit, and a quantum circuit means that I have a bunch of quantum operations, and I kind of one by one I process the qubits, and sometimes I process pairs of qubits. So I have a circuit of operations applied to qubits. And I have parameters that control my circuit, like numbers, basically. So now I have an initial guess. These would be reasonable numbers for my circuit. And again, I might be training on data. So, well, this might not be realistic, but maybe I'm trying to classify, is it a cat or is it a dog? Just like simple example. Okay, so I have data. I have parameters that control my circuit. I pour in the data. I see what percent of the time, dog, cat, the decisions were correct. Then I make modifications to my parameters and I rerun the circuit and I collect a bunch of measurements. Again, I might need to run this 10,000 times. And I evaluate with this change in the parameters, was there an improvement? But it's not that I make a single change of the parameters. I make multiple changes of the parameters. And my classical algorithm, a classical machine learning algorithm, is trying to learn what changes to the parameters that control this quantum circuit will yield a good differentiation between cats and dogs. And this sort of technique works well in the regular machine learning world, the classical machine learning world, and it works well on on quantum machine learning. And what's important for you, Joe, and for people watching at home to understand is that this is now a complicated system. You have a classical algorithm. The classical algorithm says, these are my parameters. In order to run the quantum circuit, I need a bunch of classical processing to translate from those parameters to actual commands that are given to the quantum computer. So a bunch of algorithms are run on regular computers, and then you run it, perhaps 10,000 times. You collect your data, and then you did that on one set of parameters. Now you have another perhaps 10 sets of parameters, random or not so random perturbations in the parameters. Again, you repeat all of the process back and forth from the classical machines to the quantum machine, collecting measurements 10,000 times. And now you try to analyze, again, in the classical world, what was the good choice of parameters? What do I do next? What are my next 10 experiments? So this is called a hybrid system, that you're having both classical computers and quantum computers. And It's widely thought that in the quantum world, hybrid systems are going to be around for a while. A lot of the calculations, a lot of the simple stuff that we do on, well, less complex stuff, I should say. A lot of the less complex stuff that we do on classical computers, we've been doing this for 70, 80 years, and it's been heavily optimized and it works very well. I mean, if you think about it, in our phones, we have multiple transistors for every person living on the planet. So it's amazingly advanced. So that's not going away. We're going to keep running classical computers, and the classical computers will be part of a loop that includes the quantum machine, sort of in the middle of the loop. And we're going to be running the quantum machine, collecting data at the output, analyzing that data. And the analysis will be primarily performed using the classical machine learning types of ideas.
Hmm. Well, so you've talked about this in a few different ways, but I'm curious, what do you think the future of quantum computing is? What does the future look like?
More qubits, qubits that are less noisy, more quantum error correction. We only had, to the best of my knowledge, there was a paper in 20, not sure, I think it was 2023. There was a paper that came out and showed a working quantum error correction system. So they showed that the error rates of the corrected system were better than the raw error rates of the raw qubits. And that was just, I think, in 2023. And that required a lot of quantum computation. And since 2023, we've had better demonstrations with better quantum error correction codes, and everything keeps improving. That's part of the future. Part of the future is probably going to be better quantum algorithms. Uh, I would like to think that part of the future would be that better error mitigation gives us another factor of 10 reduction in the number of shots, which would reduce the resources needed to run this stuff. Because in theory, it would be, well, super great to have 1 million physical qubits and to run error correction on them. And maybe there's a 100-to-1 ratio of overhead because of the error correction. So maybe physically we would have 1 million particles, but maybe we would, after the error correction, we would be working on 10,000 corrected qubits. And 10,000 would be enough to do a lot of things. But that's, okay, I don't want to call it wishful thinking. That's a good scenario. We're not at 1 million yet. We're at a few hundred. What if we're stuck at 1,000? That's hard to predict. It would be nice to reach 1 million, but some good things will need to happen to do that.
Hmm.
So yeah, where's the future? In terms of the applications, well, probably the best known quantum algorithm is Shor's algorithm that can be used for cracking codes. And I imagine that most of your viewers will not be happy with their emails being read, but okay, that's the world that we live in. Then there are different applications that people watching at home will probably be very happy. What about quantumly simulating chemistry systems? What if those quantum simulations of chemistry systems, what if those are actually pharmaceutical systems and we get better drug design? Last year, I heard a presentation by a quantum company at a conference where they said that and this was a material engineering type of problem. They started with something like 1 million candidate molecules. I don't remember if it was a bit more or a bit less than 1 million, but order of 1 million. And in several rounds of combination of machine learning and quantum simulation and various stuff, they narrowed this down to 2 or 3. They produced them and they had it running in the lab within a week. So it was obviously what they told us was a good scenario, right? Obviously they're trying to look good. Okay, of course. But the fact that you go from 1 million candidate molecules to 2 or 3 working in the lab within a week is, if we can get there with the pharmaceutical companies and other chemical processes, if we can get there over the next decade, that'll obviously be a better reality.
Yeah. Well, George, thank you so much for taking the time to share your research and your insights and your thoughts about the future. And I hope we can continue the conversation down the road.
Okay, thanks a lot.